Now we'll consider inclination change maneuvers. Let's assume that we've already launched into a 176 kilometer circular orbit from the Cape, and we launched at an azimuth of 90 degrees, so we are due east, and again ignoring the effect of Earth's rotation. Let's calculate the velocity change maneuver, which I'll call delta V inc, to drive the inclination to 0. Okay, so here we imagine, our original orbit. We're launching directly into the page here, and we end up with this orbit plane, which of course contains the center of the Earth, as we mentioned. And we want to end up in this equatorial plane. Okay, that's where we want to be. We launched with this velocity v, and we want to keep that velocity the same, so we want to end up with v being in this direction, in the plane of the equator, and we want the inclination to go down to 0. So we have this velocity vector. We start here and we want to end here, and let me draw that over here. Then here's the starting velocity, here is the ending velocity. We want the same magnitude, different direction, and the direction change is I. Now we can, and the delta v we want to do is this delta v right here, to go from here to there, delta v inc. And we notice that inside here, if we split this in half, this becomes two right triangles together. And so we have I over 2, here's the right angle. And we can solve for this side by v times sine of I over 2 equals delta v over 2. This is half of the value we want, because we split this isosceles triangle into two right triangles. And so we have v sine of I over 2 is delta v inc over 2, or doubling this, we get the solution. The delta v inc is 2v sine I over 2. Let's compute some numbers. So if we're in this circular orbit at 176 kilometers altitude, the velocity we know is 7.799 kilometers per second. The latitude of Cape Canaveral is 28.5 degrees. Plugging these numbers into our delta V inc equation, here we have the circular speed, here we have sine of half of 28.5, and we get a delta V to change the inclination from 28.5 to 0 is 3.839 kilometers per second. Inclination change maneuvers are typically costly. This is a big number. This is a very costly number in terms of propellant. So we'll consider later on if there are some more efficient ways of making an inclination change. In the example we're going to look at now, we'll see how that can be reduced. We'll look at a transfer from an inclined orbit, an inclined low Earth orbit, to geostationary orbit. We note that a geostationary orbit, or GSO, is a circular one sidereal day orbit with zero inclination. By one sidereal day, I mean 23 hours, 56 minutes, and 4 seconds. It's not a 24-hour day that we're interested in. We're interested in the time it takes the Earth to rotate once inertially, not once with respect to the Sun. And so that's a little bit less than 24 hours. So that's the orbit period we want. And we'd like to have zero inclination, so we want to be in the equatorial plane. Now, by the way, there's a difference between geostationary orbit and geosynchronous orbit. Geosynchronous includes more orbits, because it allows an orbit that can be elliptical as long as it has the same period of one sidereal day, and it can be inclined. Now, because a geo can be elliptical, you can have east-west drift when you look at the spacecraft from the Earth, and it can have north-south drift because of inclination. And sometimes you don't want that drift. you want the spacecraft or satellite to appear to be fixed over the Earth, and that's when you want the geostationary orbit. So let's look at a calculation of the delta V to transfer from the 176 kilometer circular orbit with an inclination of 28.5 degrees to a geostationary orbit.